Resource management and scheduling are some of the most common operations that happen automatically in a distributed system or ecosystem. But such operations can have different durations of enforcement and can occur at different rates. Short-term approaches refer to resource management and scheduling operations at timescales similar to the main events happening in the system, because many distributed systems respond to short requests or to jobs taking a matter of minutes to at most hours to run. This is also the duration typically associated with short-term approaches. For example, it is common to take scheduling decisions every 2 to 5 minutes for jobs that run for seconds to hours. Long-term approaches refer to resource management and scheduling operations at timescales much longer than the rate at which main events happen in the system. For example, capacity planning is typically done once every few months or even years. Currently, ordering, shipping, unloading, and configuring new physical machines cannot be done much faster. We focus in this module on short-term approaches and give only some examples for long-term approaches. Let's focus on a short-term scheduling approach. In this example, creators develop digital services, so just software and data. You may play Pokemon Go, but also use digital services such as Netflix for movies, Dropbox for data storage and retrieval, and so many others. But how do these digital services run? To run even one digital service, hundreds more software services designed and built by teams with diverse development and operational practices need to work together. They do so typically without the system user even noticing. This is a vast distributed ecosystem. Each software service needs computers to run on. The data needs computers to be stored on. Both software and data need networks between them to reach the users. We call these needs workload. Over time, the workload, and thus the amount of needed computers, varies. For example, more if there are more users, and less if there are fewer users. It is typically very expensive and inefficient to own many computers for only one digital service. Instead, data centers encompass many computers, today up to tens of millions in one place, and can share these computers across many digital services. So digital services get or provision as many computers as they need, when they need them, and only for as long as they need them. This is called elastic scaling, and it is very efficient compared to owning the computers. It is also relevant that data centers can operate at various scales and in various locations as full or micro or nano data centers in a digital continuum. Data centers have to be very efficient because they already consume about 3% of our energy. This is already more than many other industries. So an essential component of the modern data center is the scheduler, which is at its core an algorithm that decides at runtime which part of the workload and which service should run on which computer and for how long. You do the same thing when you schedule your daily activities, but data center schedulers do this at a much larger scale and with amazing frequency and sophistication. Only when the scheduler takes the right decisions can the data center operate with desirable non-functional properties such as high performance and dependability, high efficiency and sustainability, and ultimately societal effectiveness. Let's look now at an example of long-term decision-making. Long-term decisions respond to needs that do not normally arise or change rapidly. For example, the cost of electricity. We start by noticing the continued increase in electricity expenses at the beginning of the 2020s. Not only have electricity costs increased, but these roaring 20s have also brought a realization that large-scale carbon emissions are damaging our climate. So various governments have agreed to tax CO2 emissions at rapidly increasing costs. But these cost increases are highly abstract, so how can we quantify their impact on any specific data center? Using, for example, the OpenDC simulator, we can analyze the impact of increasing electricity and carbon emission costs on the financial risk to which our exemplary data center is exposed. In other words, we can estimate the cost of these increases on the monthly bill of this data center. Before the cost increases, scenario October 2020 in the figure, other costs dominated this bill. In particular, the agreement to offer high availability led to the highest cost, either because many more machines needed to be powered to ensure that the services are highly available, or because shutting them down would trigger costly financial penalties for not being able actually to deliver high availability. Note that another high cost in the figure, the bar depicting the cost of CO2 emissions to the society at large, related to health and other impacts, is typically not paid currently by the data center operators, although it is quantifiable with scientifically proven methods. After the cost increases that went on through 2021, to the 2020 cost we see significant increases to two categories: costs resulting from electricity demand in the data center, where electricity is needed to power computers and other support machinery, and from carbon emissions. Of these two additional costs, by far the most important in financial terms is electricity. We see that with the prices at the end of 2021, electricity expenses could become the primary risk in operating data centers, the highest cost. So what can data centers operators do? Data center operators could mitigate risks related to electricity by adjusting their topology. In particular, they could downscale the topology using much fewer machines and thus consuming way less electricity. But with fewer machines available, risks related to other aspects, such as not fulfilling the service level agreements and thus paying more penalties, could rise. Intuitively, a data center also cannot avoid all risks by shutting down all its machines. This would mean stopping all its core business and paying high penalties on all running contracts. Exploring this trade-off is the job of a long-term approach to capacity planning. In this example, we used OpenDC again, with the figure depicting the main results. We considered various topology scales relatively to the data center used when we discussed the impact of increases in electricity costs. Energy efficiency is important in such estimations. Whereas an efficient data centers could use all the input energy to power its computers, less efficient data centers could easily use up to 50% more energy to power the same computers. So, in our experiments, we also considered various classes of energy efficiency, taking as settings the best-in-class efficiency reported by Google, the average efficiency reported by the industry, and the low efficiency typical of many small and mid-sized data centers. Our experiment suggests that no matter which energy efficiency class of the data center, with the current electricity price increases, the compromise, the trade-off, between topology scale and SLA compliance is actually complex and must be explored. The wrong choice is almost 5 times more costly than the best result found in this exploration, and this happens for both too small and too large topology scales. This is our first finding. The shape of each curve in the plot also indicates that there exists an optimum. This optimum is different per class of energy efficiency, but overall it results from adequate downscaling of topology scales. There is room to use fewer machines, which is our second finding. We conclude here the discussion about short and long-term approaches. Both are useful, but they operate at different timescales and thus typically employ very different resource management and scheduling techniques.